Model-based engineering techniques are today's emerging practice to realise digital engineering, an engineering vision to shift the design of complex systems to be based on digital representations that enable digital analysis and reasoning of systems without the dependency on actual physical prototypes. The premise of digital engineering is to shorten project times and save significant costs comparing to the non-digital practices. Model-based systems engineering is the utilisation of digital models to support the decisions and work products of systems engineers. Key goals are to elaborate and validate requirements, to develop system architectures, to allocate system functions to components, and to produce interface control documents that specify the interfaces that each system component needs to support. Systems engineering level models can also be further elaborated towards software development, where they can automate the production of source code from models or visualize an implementation by reverse engineering existing source code. Here in our demonstration, we'll be looking at an adaptive cruise control system designed with an MBSE approach. We'll see how models are built following the IBM Harmony model-based systems engineering workflow. Now, whilst the core of this demo will be focused around the systems model, we will also see how the modelling activities are integrated with other supporting systems engineering activities, such as planning and tracking, requirements management, test management, and reporting. Here, the Harmony MBSE workflow is visualised with deployable, navigable practice content that guides the systems engineer through the various activities and tasks that need to be performed when building a systems model. We can drill down from high-level activities to detailed descriptions of tasks that need to be performed and how to perform them. That guidance is then realised with a plan in the task management part of the platform, that's Rational Team Concert, that tracks the activities of the systems engineer. Here in Rational Team Concert, we're looking at plan data for the adaptive cruise control system. If we drill down into this ACC Systems Engineering Development Plan, we can see all of the tasks described by the MBSE workflow practice content that our engineers have to perform to develop a systems engineering model. As that model is being developed, model elements are connected to the work items for traceability. For example, Dave is our systems engineer. One of his tasks is to define use case scenarios. If we open that task and take a look at the Links tab, then we can see all of the scenarios modelled as sequence diagrams in the model that have been connected to this task. We can even view those link design diagrams right here in Rational Team Concert using Rich Hover, a common capability across the Jazz platform and a huge time saver. Engineers can view any kind of linked data without leaving their current tool. Let's click on one of those link diagrams to open it in Rhapsody Model Manager. That's the architecture management part of the platform where the models are stored. We're now in Rhapsody Model Manager, or RMM for short. Here, models may be viewed and browsed using only a web browser. No desktop client is required. Stakeholders and domain experts can review specific areas of the model without any knowledge of how the model was built or how to navigate around it. They can simply follow a link in an email or a connected work item to be taken to the exact part of the model that they need to see. One of the reasons for building a model is to elaborate requirements, and this is one of those cases. Here in the links section, you can see that this sequence diagram not only elaborates work items, but it also refines requirements. Now, later in the lifecycle, you'll also want to perform verification and validation activities. So this sequence diagram is validated by a test case in Rational Quality Manager, the test management part of the platform. We'll see that later, but first let's open a linked requirement. Here in Doors Next Generation, the requirements management part of the platform, we can see a module or document of system requirements. These columns show how those system requirements are connected to the models. In the Harmony MBSE workflow, we use specific link types and we link to specific model elements dictated by that workflow. For example, system requirements are first traced to use cases. Then a functional model is built for each use case. And in that functional model are scenarios, modelled with sequence diagrams, that refine the requirements. And finally, in the architecture, there are operations and event receptions that satisfy them. Views like these allow the requirements engineer to identify gaps. For example, at least one of these system requirements has no associated sequence diagram, and there are others that haven't even been traced to a use case yet. Let's go back to architecture management and take a look at the linked test case. Part of systems engineering is the system verification and validation, or V&V, activity. V&V is managed by Rational Quality Manager, a collaborative hub for systems and software quality that specifies and tracks the system's test plans and their execution. V&V is tightly related to the system elaborated requirements, as described in the MBSE model. The V&V activities also relate to the system components that are captured in the MBSE model. Hence, MBSE model scenarios trace to test cases, and their test plans should relate to the system development plans for the architectural components described in the MBSE model. Now, we've seen how a sequence diagram is connected to requirements in Doors Next Generation and test cases in Rational Quality Manager. Let's open the model in Rhapsody, the desktop client, and dive a little bit deeper into how the model was developed. This sequence diagram is a specification for how the system, that's the vertical lifeline in the centre called UC Adaptive Cruise Control feature, should interact with elements outside the system context. In this case, that's the driver and the engine controller. In this scenario, when the driver presses the brake pedal. And this scenario forms part of that functional model that I mentioned earlier. Sequence diagrams can be used to guide the designer as to the behaviour of the system, and they can also be used to later test that same behaviour. They also form the basis for defining interfaces. Now, we'll see all of that a little bit later, but first let's look at the model context. This diagram shows us an architectural view of our adaptive cruise control system. That's the green box, and the elements it interacts with. Those are the orange boxes on the left. In this case, that's the driver, the forward vehicle, and another part of the car, the engine controller. The diagram also shows us a detailed view of the adaptive cruise control system. That's the blue box on the right. And it's listing all of the operations or internal system functions that the system can perform. How and when it performs those functions is determined by its behaviour. In this case, that's been modelled using a state machine. State machines describe the modes or states of the system and how and when the system changes state in response to stimuli, and what it does when that happens. Usually that's triggered by the system receiving a message from something in the system context, and that communication is detailed in the sequence diagram we saw earlier. Later we'll see how that model can be verified and validated through execution, but first let's see how the model is integrated into the rest of the lifecycle. We saw some of that traceability in the web client, which is very useful for requirements engineers, domain experts, and other stakeholders. Model builders can see that traceability here in the desktop client too, and that traceability can be represented in many different ways. For example, this requirement coverage table shows us the system requirements from DNG, and the use cases, sequence diagrams, and functional model features that cover them. This makes it very easy for the modeler to spot gaps in their traceability, or to spot requirements that they have yet to fully model. Of course, we can create tables to show this information in any way we like. Let's take a look at a few more examples. This one shows us all of our sequence diagrams and the requirements that they refine, making it very easy to spot which sequence diagrams are not yet connected to any requirement. This table shows us all of the work items that have been connected to model elements, along with key attributes such as their priority, status, and so on. We can show things graphically too. This diagram shows the sequence diagram and the requirements that it refines. It also shows the operations of the functional model represented in this scenario and the requirements that they satisfy. Lastly, it shows the system requirements that have been traced to the use case that is the parent of this functional model. Now, in theory, all of that traceability should match, but diagrams like this allow for consistency checking. In this case, for example, the deactivate VDS function satisfies a requirement, but that requirement was never traced to the use case for this functional model. Now, that's an inconsistency that the modeler needs to resolve. Models can be used to verify and validate our understanding of the requirements, to visualize the system, to specify the behavior, the architecture, and the interfaces of the system, and of course to document design decisions. They act as a single point of truth, and as such can be used to automatically generate many kinds of physical document. Rational Publishing Engine is a document generation capability that can produce federated cross-domain reports from across the CE solution, including the models. Here we can use a simple wizard to pick a template. In this case, let's choose ICD, or Interface Control Document. That generates a report in several formats at once, including PDF and Word. Now we've seen how models are built, traced to work items, requirements and test cases, and used to automate document generation. Let's now take a look at how a defect raised against an already released system might be investigated, tested, and fixed using model-based techniques.